time is it? Guess we got a few more seconds, yeah.
We have a test after this chapter. Or...
After this chapter, yes. 1 and 2? Yes. Yes, indeed. But we're gonna do a quiz on units, unit conversions. So I got to figure out how to use Canvas first. So I'm gonna put a quiz on there so y'all could do it like from wherever. You know what I'm saying? But you're gonna have to use Canvas. Oh, it's not a lot of people in this class, so uh I can handle this class. How many? Like 7?
Yeah, probably.
Yeah, I can handle y'all. So I might not. I might just go old school with y'all. It's a little rougher old school, but it turns out better for you. All right, how you doing? The multiple choice tests and all that kind of stuff. It's not a good thing in physics. Trust me on that. But for my physical science class where I got 50 something students, I just simply can't grade that many tests. It's too much. All right. But I wonder if I can. Maybe y'all might be a little bit more savvy with this than me. I wonder if I could just record it directly from here. That's a good question, man. Let me see. That would work so much better. No, I don't have to write it down. Oh, yes, I do. No, that's a USB. All right. Maybe I'll try. I'm gonna try next time. Bring my adapters. Good morning. All right. Then let's put it right here. Let's open up. right. All right, so as I just mentioned a few minutes ago, so we gearing up for our first test, right? Chapters 1 and 2. Okay, so we're gonna jump into chapter 2 today. All right. The best way to learn chapter 1 is to jump right into chapter 2 because you got to do a lot of chapter 1 in chapter 2. Okay, so we're just gonna jump right into it. And as we recall, chapter 1 was unit conversions, right? Unit conversions. That was chapter 1. That's what we dealt with mostly in chapter 1. Unit conversions. Okay? So, we're in chapter 2 now, and let's do this. And maybe this will make it better for the folks. Can we it ain't gonna get too scary in here, huh? No, this here. We can't turn the lights off in here. On that side? Let's see. One more time, but after that, we might keep it moving. All right. Good afternoon. All right, so we're in chapter 2. We're talking about motion in one dimension. All right. What the? Somebody been eating some candy or something. What the hell? Oh, he's gonna do that. All right, so we're in chapter 2, motion in one dimension, right? So that means motion in one direction, okay? And that could be in the horizontal direction or the vertical direction, okay? So the contents of chapter 2, we're going to talk about reference frames, talk about average velocity, instantaneous velocity, acceleration, motion at constant acceleration, and we'll solve some problems, and we'll start talking about free fall. All right? And then we'll do some graphical analysis of motion. Okay? So, what's a reference frame? All right? So any measurement of position, distance, or speed must be made with respect to a reference frame. Right? So whenever we talk about how fast something is going, how fast the car is traveling, right? That is with respect to the earth, okay? When we talk about how fast a car is traveling, we're talking about with respect to the earth, because the earth is the reference frame. All right? So the same way, if I'm sitting on earth and I see a train pass by and someone is sitting on that train, or we have several people sitting on that train, or some people sitting, some people standing, some people sitting still, some people moving, right? Well, when I'm sitting on the earth, the motion of this person here doesn't look the same to me on the earth as these two people sitting right here. Why? Say what? Not different movements. Huh? No, they don't have different speeds. They don't have different, well, yeah, they got different positions. But y'all listen to what I'm saying to you. Y'all not considering everything I just said. I say if I'm standing on the earth, on the ground, why does the speed of this person look very different to me as the speed of this person to them?
Oh, the direction of the train?
Well, it's because they're both sitting on the train. Yes, they are on the train. These two are on the train. That's why what they observe with his motion is very different from what I observe. Because I observe his motion on the train as well as what? The train's motion. Right? Okay. So, that's why we make a distinction between distance and displacement. There is a distinction between distance and displacement. Right? Distance is what it is. It's exactly that, right? It's distance. Is how, distance or how far did I go from point A to point B? That's distance, right? Displacement is the difference between my starting position and my final position, right? Can we think of an example where we start and end up in the same place?
Race.
What?
A race around the track.
A race around the track, right? A race around the track. So, so let's say a person ran around the track, a 400-meter track, twice. What is the distance? What is the displacement?
It's a trick question because I mean that's the starting point from the starting and the ending point, right? Is you saying like what place they gonna be in or might be
Zero. A lot of times when it's a trick question, I mean you said it, right? You just gotta connect it next time. When it's a trick question like that, right? That's the first thing you should think about. Is the number 0. So if a person ran around a track, 400-meter track twice, they started and ended in the same spot. So their displacement was 0, but the distance was what? 800 meters. You saw them run around the track 2 times, but the displacement is 0. There's a difference between distance and displacement, and that's what's going to define the difference between speed and velocity. So far we've been talking mostly about speed, how fast something is going, right? Velocity is how fast and what? No. How fast and in what direction? Say what? You got a question? I said velocity is how fast the object was traveling plus the direction in which it was traveling. That's the difference between speed and velocity. Speed is just what? How fast. velocity takes into account your direction. Very important. So if we look at the cartoon right here, right, then we could say that this person's displacement was what? 40 meters, right? But what distance did they cover to get to that 40 meters? No. No. 100. I said, what distance did they cover to get? Yeah, what distance did they cover? Right? Not the displacement. The displacement is 40. We started out at 0, we ended up at 40, but we went way out to 70 and came back to 30, and came back 30 in the opposite direction. Okay? That's very important. That's very important. So there's a difference between distance and displacement. Same difference here, right? We look at the two cartoons. We have on the left-hand side, we're going from 10 meters to 30 meters, right? That's a distance of what? 20 meters to the right, right? Or in the positive direction. So we have a distance of what? On the left-hand side. What's the distance here? 20. Okay? And we're traveling in the, which is east, right? East, west, north, south, right? So we're traveling east 20. And so on the right-hand side, what is this person doing? They're traveling west, right? But they cover the same what? Distance. But they have a different what? Displacement. Yes, indeed. All right? So, like I say, that leads us to some equations on distance, right? Distance or speed, average speed, right? Speed, how far an object travels in a given time interval. Speed is distance divided by time elapsed, right? Velocity includes direction. You must have the direction when we're talking about the velocity. Right? That's like if I asked you for directions to your hometown, and you weren't from Baton Rouge, I asked you for directions from your hometown. And you told me, oh, just get on the interstate and go 200 miles. What's wrong with that? There's no direction.
Cause how you know I gotta go 200 miles?
Well,
Which way am I going for 200
which
miles?
way am I going 200 miles? Because 200 miles could be in either direction. Okay? So it's very important that we specify a direction when we talk about velocity. Okay? And so if we look at the two cartoons here, right? This slide is actually talking about instantaneous velocity, and we're not going to deal with that. That is a calculus concept, right? So we're doing algebra-based physics here. So we're not going to deal with this, but it's here because they want you to understand that there's a difference between average velocity and instantaneous velocity, right? So if I look at the cartoon on the right, how fast am I traveling? On the left, I'm sorry. 40 kilometers per hour, right? And that speed remains what? Constant. Because it's a straight line. It's a straight flat line, so it remains constant at 40. So that means that throughout this time interval, right, along the path from here to your hometown, I could tell you exactly how fast you were traveling, right? Now, with the situation on the right, what happens here? We start at what? 0. We shoot up to 50. We stay at 50 for a little while. Then we do what? We drop down to 20. Then we stay at 20 for a little while. And then we ultimately do what? Stop. So, then if I said, all right, well, if we take an average velocity, which is 40, because it's showing you right here, right? Well, I could say, oh, well, what's a 20% of what is that, about 12 minutes or something like that? I don't know. So 15 minutes. 15 minutes in the drive. I want to know, well, how fast were you traveling at 15 minutes? Can you tell me? No, you can't tell me. Right? All you can tell me is an average. Right? We're doing average speed. Right? In order for you to tell me how fast I was traveling at 15 minutes, right, you would have to do calculus or a first derivative. But like I say, we're not going to deal with that. But I just want you to realize and understand that concept, that one is an average speed, right? It's like me going to your hometown and I did the speed limit the whole way. On this side, I burned rubber for the first 50 miles. I saw the police, slowed down, right? Saw them I saw them slow down to 20, and they got behind me, and I stayed at 20, right? The rest of the way until I made it to the house. Okay? So the speed is changing here, but here we have it constant. That's a much easier situation to analyze. And that's what they're showing you right. We have a cartoon which this actually talks about acceleration, right? So what is accelerate? What does it mean to accelerate? What does that mean? Huh? To go faster or change speed, right? Which could be what? Going faster or slower. That's what acceleration is. It's a change of velocity. So something can be moving but not accelerating. Correct? And so just like velocity is a vector, right? And what a vector means is you must specify the direction. If you don't specify the direction, oh, that microphone is working. If you don't specify the direction, then it's meaningless. You have to specify the direction of acceleration. When we're talking about gravity as an acceleration, what's the direction? Down. Gravity works down. That's it. It only works in one direction. All right, so there's a difference between negative acceleration and deceleration, right? We could be accelerating and going in a negative direction. That's not the same thing as a deceleration, though. Y'all following what I'm saying?
Like going down the hill,
Huh?
like rolling back on the hill.
So a negative acceleration let's say let me use this one. Let's say, and maybe I should catch this with the camera as well. And maybe, let's say I have a coordinate system, Cartesian coordinate system. This is Y, this is X, right? And I said, okay, I have a car, and it went, right, west, east, north, and south, right? So I could start from right here. Say for instance, I start at here. This is a what? Negative 20. Y'all follow what I'm saying? This is 0 right here, right? That's 0. So all numbers this way are what? Negative. So I could be, my car is here, and I say the car accelerated in the westerly direction. Right? When it got here, to this point, it was what? Negative 60. Right? Because we're going further and further west. So I'm going in the negative direction, but I'm accelerating. You following that? Now, deceleration is me doing what? Slowing down. That's the difference. You see the difference now? Did I make that clear for you? Deceleration is slowing down. It's not the same thing as a negative acceleration.
So if you were from like 20 to 15, that would be deceleration?
Yes. All right, so back to our slides. I'll keep that up there, whatever. All right, so again, here's a calculus-based thing. We're not doing calculus. We're in algebra-based physics, so we're gonna skip this. But it's the same principle that we talked about before. The difference between average and instantaneous. Okay, but we're skipping that. All right, so remember what I said to you. I say what two things do we need to describe the motion of an object? What were they? Two things we need to describe the speed, motion, velocity of an object. What are they? Distance. I just asked you. I say I use velocity. No. Distance and time. I said, what two things do we need to have in order to solve for the speed, right? The speed or velocity. Velocity is the speed with the direction on it. Right? So that's what's showing here, right? We have a change in position, which is a distance. If I change my position, that means I covered a distance. In order to change my position, I got to cover a distance. And I did that over a time interval, t. And the same thing is true for acceleration. If I change my speed from v to v naught, right? Remember what I told you about naught, v naught, v naught, v naught means initial velocity. The velocity when I first started off. And so we could do some algebra and some things drop out here and there and blah, blah, blah. And we come up with the free fall equation here. That's the one we worked with on last time, right? Everybody remember this equation? This is the free fall equation. And so now we have free fall, the free fall equation, which is very powerful. And we remember this equation too, right? What do we call that one? The golden rule. All right? This is just the average velocity, right? If I take two things, add them together, and divide by 2, that's called the average, right? If I have 10 things, I add them together and divide by 10, that's called the average. And here is just the acceleration equation written in terms of the final velocity.
You talking about the first one or the 100?
211.8, right?
That one called acceleration.
Yes, right? Because acceleration is equal to v final minus v initial. Sometimes they don't put the f, right? They just put v over t. So if I rearrange this equation for v, I'm going to get v equals v naught plus a t. Did everybody follow me with that algebra? Or did we get lost? Who said that? So we're gonna have to knock the rust off with the algebra, right? We got problems with algebra. We need to work. It's gonna continue to be a problem. We got problems with algebra. Okay, so we're gonna have to get some practice. All right, so you have a list of 4 equations here. Okay, very powerful equations. You're gonna need them. Okay, when we solve some problems. Okay. Speaking of solving problems, here we are. Okay, there's a problem-solving procedure. A lot of times, particularly when we have trepidation with mathematics, when we see a word problem, we start to experience a lot of different emotions, from fear to all kind of things, right? Kind of like going to another country and you don't know how to speak the language. Okay? So, if you're that person, then I suggest you follow these steps every time you do a problem. And it's going to become second nature to you at some point. All right? So, go through these steps every time you do a problem. Okay? Trust me on that. I've been doing this for over a decade, right? So I know what works, particularly for people who have problems with mathematics. Okay? And keep in mind, these slides are available to you on Canvas. So you can download these slides. And all of the courses are recorded, or all of the classes, lectures that I attend, right? Because sometimes I'm on travel. But all of the lectures I attend, which I attend most, they will be recorded and put on Canvas. So you can go back and you can look at these things and you can study, right? You're not going to get it one time. Trust me. Trust me on that. You will not get this stuff one time. By coming to class, sitting here, and listening to me talk about it, you will never get this. It does not happen that way. Not in this class. No way. You're going to have to bump your head on your own, figure out what it is you don't know. And then you come back to me and you say, I don't know this. This is what I don't know. You see? Or this is what I have a problem with. But if you never do that, then you know when you're going to find that out? On test day. And then on test day, I can't do nothing for you, right? So, again, these problem-solving procedure steps or problem-solving procedure is there for you. Download it, look at it, practice it, okay? So, free fall. So, we've been talking about free-falling objects, right? Near the surface of the earth, all objects experience approximately the same acceleration due to gravity. So what does that mean? All objects experience the same acceleration due to gravity. Sure. So, question. If I have a bullet in my left hand and I have a gun in my right hand and I shoot the gun and drop the bullet at the same time, which one hits the ground first?
The bullet is in your left hand.
Why?
Cause you say you shot the gun. You didn't say which direction either.
I didn't need to. Now that's a good thing. I'm glad you said that, but I didn't need to in this case.
But you didn't say you shot it at the ground. So that bullet could be traveling forward.
No, I pointed how I shot it. I shot it horizontally.
So that means it's probably bound to impact something. So that bullet in your hand gonna fall to the ground first.
The bullet at the gun got a constant, it's like a constant acceleration, so it's just gonna go straight.
Faster.
They both have a constant acceleration
Gravity pull.
due to gravity. So, my question is, y'all still ain't answered the question. Which one hits the ground first?
The one that you drop.
Why wouldn't he?
Y'all just answered it. Y'all told me what y'all just told me. They both have what?
Gravity pull. Gravity.
They both experience gravity. And gravity only pulls what?
Down.
Down. So you saying that because I shot the bullet, gravity is not going to pull it down?
It's gonna pull it down.
Okay. If I drop the bullet, we know it's going to pull it down, right?
Yeah.
And I just told you what?
They got the same acceleration.
All,
So both of them gonna hit?
what?
At the same
All objects, regardless, it does not matter what it is. I said that before, right? Doesn't matter what it is. Whatever I get on, if I get on that was in my previous class. That's what we was doing. If I get on the Golden Gate Bridge and I drop a penny or a bowling ball, they both will accelerate towards the earth at the same rate. So again, let's ask the question again. Which one hits the ground first? They hit at the same time.
Wait, so you shot the gun at the ground?
No, I just said I shot the gun horizontally.
Both of them got the same acceleration, cause so they both gonna hit the ground at the same time.
Yes.
So it's not gonna go straight.
Oh no, it's gonna go straight.
Go, but it's gonna hit.
It's gonna hit the ground though. You gonna see that one hit the ground, cause it's gonna go straight down. But the bullet, you ain't gonna see it, cause it's gonna go forward, but it's gonna hit the same time as this one.
So, well, never mind, cause you told me they got the same acceleration. So that wouldn't matter. I was gonna ask something that you was gonna say, well, you just answered your own question.
Well, let me see if you answered your own question. Tell me what you was about to ask me.
Basically, I was gonna say, so if the bullet go out first because it's pushing the air, it's gonna push it out faster than you dropping it. But you saying they got the same acceleration.
Okay. Well, the difference. Oh, that's actually a good question. You see,
Oh, see,
and you didn't answer it actually, but that's a good question,
To
huh?
answer that.
Yeah.
You shoot the gun in the air, and you drop the bullet in your hand.
Let's deal with her first. So you said because the air you hit it and it's going this way, right? Well, in which direction did you hit it? So what does that have to do with this direction?
Down. Okay.
Now what you got?
You shoot the gun in the air, and you got that bullet, and you drop it in your
I
hand.
didn't shoot it in the air. Don't change it up. You changing it up now. I said I shot it like this.
I don't even see how it's gonna hit the ground. You gotta hit something.
What you mean? So you saying if you shoot a bullet, is it stay in the air forever?
You say you
So if a policeman shoot a bullet at somebody, when does it stop? Does it ever stop?
impact. When it hit you, it's
So what if it don't hit nothing?
It's gonna drop.
It's
gonna
gotta
drop.
hit the ground eventually.
It's like some people miss shots. In the
Yeah.
body. It's wrong.
Keep thinking. That's what I want. That's what I want you to do. Yes, sir.
So what you saying? So any object, right? So what you saying is if you do drop a bullet bomb and you drop a marble, doing it at the same time?
Yes, sir.
Okay.
Yes, sir.
But they gonna have the same acceleration.
Yes. If I drop a marble and a comet. Well, I couldn't hold a comet, but you know what I'm trying to say.
But we still talking about on Earth, right?
Yeah, you got to be
Okay,
on
that's
Earth.
what I'm making
Yeah,
sure.
you got to be on Earth.
Because
Near.
that's
That's what it says, right? Near the surface of the Earth. Right? Why is it? What's the two most dangerous situations in a plane ride?
Going up, going down.
Ain't going down.
Why you think that is?
Cause going down, you gotta
gotta-
decelerate.
No.
You
You're
gotta
thinking
keep
too hard.
accelerating.
You're thinking too hard. We're going too hard. It's a very simple answer.
Now, land first.
Yeah, of course we gotta land.
Where the land at? That's why I think you know.
No. We're in physics class. We're talking about physics. Why is it the most dangerous part of the flight? Taking off and landing.
Gravity.
Because you're going against gravity, and the other one you're doing what?
Coming down.
You're going with it.
Got you. Gravity.
Okay?
Crazy, but I ain't teaching all this in school.
But y'all never been taught by a scientist.
I see.
Y'all been taught by the high school physics coach, the math teacher. You know, I'm a scientist for real. I do science for real. Material science and engineering. I'm actually an engineer, but I have a degree in physics though. So look at this cartoon. What's the difference here?
The weight difference.
Nope, not the weight. Because remember air resistance. Because we just said it. He just said it earlier, right? If you drop a marble or a bowling ball, they both gonna hit the ground at the same time. Well, why don't
Paper.
the paper and the ball hit the ground at the same time? Because the air resistance makes the paper do what?
Float.
Float.
So that's what I'm saying. So
But even though it's floating, it's still being pulled by gravity at 9.8. It's the air resistance in the opposite direction, right? Because that's what air resistance works. When gravity is pulling on something, the air resistance is working against the gravity. So that's why it's doing this. And eventually it's going to do what? Hit the ground. So ultimately gravity is going to win. Right?
So, Crystal, if it had like a weight thing, that wouldn't have mattered with the air resistance at all?
No, if it's had a weight on it, then the weight cuts through the air like the ball. See, that the ball, and see, even in this example, you see how at first she had it, yeah, and she made it even, so it has a geometrical consideration as well, right? Like at first it was a flat sheet of paper. So the air resistance is gonna do what? It's got a lot of surface area, so it's gonna push it a lot. But when I ball it up, it's not as much surface area, so it can cut through the air and go straight down. That's what they're showing you there. But they're both accelerating at the same rate.
Okay, one question. So what would it be called if, when both of them hit the ground, one of them, like the ball is gonna bounce, right?
Yeah, but that ain't got nothing to do with gravity. That's the ball. That's the ball. Ball bounces.
That's all.
Yeah, that ain't got nothing to do with gravity. All right. So good. That's how it should. That's how class should be. You should talk to your faculty member, and you should ask them questions. And if they can't answer your question in class while you talking to them, then they should say that. Because I can't answer every question, but I'm gonna answer the majority of them. But I can't answer all of your questions. So you should talk, right? Especially in science class. See, what we used to is some person getting up here and turning their back and writing a bunch of equations and never even look at y'all and ask y'all nothing. And I told you that's not what we're gonna do in here. All right? So this just shows us free falling objects, right? And we can actually create this plot. We could take an object, drop it, measure how much time it takes to cover a certain distance, and we can plot this, and we're gonna get that curve right there. So, like I told y'all, right? The mathematics we do in physics is real. We don't make it up. Nothing is made up. This is not Star Trek. Okay? Nothing is made up. And lastly, we're talking about graphical analysis, right? So here we're just basically learning how to interpret a graph. Right? We have position on the X, right? Position is a dependent variable. Everybody know what a dependent variable is? Okay.
Change when it's consistent.
Huh?
When it don't change when it's consistent.
No, that's a constant. That's not even a variable if it don't change. What is a variable? A dependent variable. It's something that changes in response to something else. So how does the position change, or what does the position change in response to? Time. So then that means that this is the what variable? Independent. No. An independent variable means what? Doesn't need anything for it to change. The only thing time needs for it to change is who? Who? Huh? No, religion. You said religion?
Position.
Oh, position. No. I was talking about God.
Oh,
That's the only person that affects time. That's the only thing that affects time. Am I right? Am I wrong? Time will go forward regardless of what happens. It's the ultimate independent variable. does not depend on anybody. That's why they call it what? Father time. Okay? So the time is on the independent variable, right? And position depends on how much time we are considering, right? And so if we look at the slope of that line, the slope of that line gives us what? Velocity. Good. It tells us how does the position change with respect to time. All right? Good. I think we're going to wrap it up right there. And so, like I said, we're gearing up for our first test, chapter 1 and 2, units and motion in one dimension. Okay? We're going to do some problems out of here. We're going to solve some problems out of here. And like I said, solving problems in chapter 2 is the best practice for chapter 1. Because you're going to have to make a lot of conversions in chapter 2. And that's what we're doing in chapter 1. All right? And if you haven't registered on mastering, I suggest you get that done pretty soon because we're going to eventually start assigning work on mastering physics. All right? All right.